So, in this module I will discuss the basic manufacturing processes of metallic biomaterials. So, essentially how you make the metallic implants in the lab scale or commercial scale production, and little bit about their mechanical properties, particularly how these metals behave under different modes of loading like tension, compression, shear, etc. Now, just to remind you that engineering materials, if you look at this particular slide, the engineering materials can be classified into three broad categories: metals and alloys, then ceramics and glass, and polymers, and one derived class which is essentially mixture of either metals and ceramics or ceramics or polymers and metals. So, these are called composites. So, composite is not a primary material class, however, composite is a derived material class, and three classes of composites is MMC stands for metal matrix composites, CMC stands for ceramic matrix composite, PMC stands for polymer matrix composites. Now, different examples are provided. Out of that, steel and aluminum titanium alloys are most widely used as metals in biomedical applications. There are examples of the ceramics which are given: zirconia and alumina, they are again biocompatible ceramics. Polyethylene certainly is used in biomedical applications as well. Now, these are some of the commercially available and clinically used metallic materials. What you see in this slide is a large metallic plate, titanium plate, it can be titanium plate, it can be stainless steel plates, and you can see certain holes here, and you also see certain nails there. So, this what happens, this different fracture fixation during orthopedic surgery, these nails can get into these holes of this plate, and it can be screwed against that existing bone. So, this kind of manufacturing to make metallic plates with defined hole geometry is possible in reproducible manner in case of metallic biomaterials, and that is clearly an advantage for metals over other material classes like ceramics or polymeric materials. So, in the case of ceramics and all, because of their brittleness, you cannot make this kind of hole, because simply that entire material will be shattered into pieces, but these metals, this making the different shapes and sizes of the metallic implants is certainly an advantage. There are other examples which I have also provided in the introduction of the course also, like in the total hip joint replacement, this metallic stem is widely used, that is mostly the stainless steel or titanium based alloys. These are some of the commercial total hip joint replacement materials. You can see the stem materials, and you can also this is the part of the stem, and this is the total hip joint replacement, and you can see also that acidable liner and then socket here, and you also see that femoral ball head. This femoral ball head can be made of stainless steel, can be made up of cobalt chrome moly alloys. Also nowadays ceramics are also used increasingly, like alumina ceramic ball heads or zirconia tough and alumina ceramic ball heads, these are also commercially available. The examples of different bearing couples in the total joint assembly, here we have given some examples like metal and polymer, like this metal is that femoral ball head, polymer is a liner, ceramic on ceramic, which is not that much used nowadays or rarely used because of their unreliable mechanical properties, and metal which is been traditionally used and being manufactured by various orthopedic device manufacturing companies. So, this is a close up look of this, how this femoral ball head go inside this acidobular socket and liner into the, and this acidobular socket liner, this is made up of ultra high-molecular polyethylene, that is highly cross-linked ultra high-molecular polyethylene. So, this is a very interesting example, the total hip replacement. Here all the different primary material classes are used in an integrated manner. For example, this is your polymer P, and this is the femoral ball head which can be either metal or can be ceramic, because ceramic ball head has a distinct advantage over the metals or polymer simply because ceramic has much longer durability. And when you come here, this is the neck of the femur, and then here this femoral stem, and this femoral stem part is typically made up of the titanium alloys or stainless steel based materials and so on. So, here again this is a clear example of the metal. So, this is one of the example that where all three material classes are potentially used or commercially or clinically used: metals, ceramics and polymers, and this the right hand side, this is that example of the total knee replacement. So, again there is a femoral component here and so on. Now, coming having said all, having given this particular background of this uses of different metallic materials, let me just show you now that how these metals can be processed in industrial scale production. So, now there is two routes that you can process these metals. One is the molten metal route. So, you make this steel based material, let us take the example, make the steel based materials. So, you do this continuous casting or ingot casting, you give it a particular shape, then it will go through a series of the processes like rolling to make the plates like metallic plates, or you can extrude it to make it rods, or you can make this forging and press forming, and then ultimately you need to make this this implantable metallic materials to a particular shape, and this particular shape you have to give exactly as per the requirements in the patient's defect side. So, therefore, one has to do machining also as one of the final stage, and after the machining, finishing, assembly and products. Now, finishing, assembly and products, the classical example I have given you in the last slide, that is the total hip joint replacement, where you make these metallic materials. Now, you have seen the ball head. This ball head typically requires that polishing on the top surface, and so that it will be in classic, it does not have too much rough surfaces, because rougher the surface of the ball head, the more would be the friction when this ball head will make intimate contact and will be in reciprocatory motion against this ultraviolet polyethylene. In order to avoid that kind of situation, one is to have a very smooth polished surfaces of the femoral ball head, and this polishing is a very important thing, and since it is a very geometrically complex kind of a curvature and so on. So, this polishing is not an easy things like flat sample polishing in case of traditional metallurgical techniques. So, this polishing is itself is a challenge in case of the femoral ball head. So, therefore, this machining and other kind of manufacturing techniques which are normally adopted to make some of the complex shaped device components like femoral ball head or acetabullar socket, you need to have certain series of the manufacturing techniques to in place to essentially get the final product. Another process which is kind of used not to that extent, but relatively lesser extent is the powder based processes. So, you have the metal powders, then you press it, then either you can sinter it, sinter means high tempering. I will cover in more details the sintering aspect when I talk about that ceramic processing techniques, or you can do powder injection molding and to make a near net shape product. So, this powder injection molding, the advantage is that you can get more or less near net shape product. Now, near net shape products is somehow very difficult here in a one step process in case of the molten metal based route, whereas powders, injection molding and then molding and then you can have a specific mold shape, so that you can get the implant exactly in a particular shape and size. So, manufacturing, essentially the manufacturing means that ability to create shapes, components and assembled products, and that relies on various physical phenomena, like one is the liquid to solid phase transformation, that is I have mentioned just now. This is melting and solidification. So, melting and solidification, this is one of the route for this liquid to solid phase transformation, and you can get the required shape in liquid form and then solidify. The second one is the ability to certain materials to flow under stress, like I will show you in the next one or two slides, that there is something called bulk deformation process like rolling, like forging, like extrusion, where bulk material will undergo deformation under compressive stress or in some cases under tensile stresses. So, if a material cannot flow or cannot be deformed under stresses and the material cracks, then that material you cannot make it a very complex shape. So, one of the principle that is followed, like hit them and beat them. What is the meaning of that? you heat them at high temperature, so that metals becomes ductile or metal can flow, and then beat them means then you deform them to a particular shape that you want to provide in the final applications. So, this is the second concept that I have mentioned. Third one, the ability of powders to flow like a liquid into the particular mold and then sinter. Sinter means it is a high temperature treatment. High temperature means that any given material has a specific melting point Tm. So, you have to heat at a temperature above Tm by 2 or above 0.5 Tm, and you can, if necessary, you can apply pressure also, so that under application of pressure this material will be densified and will be shaped into a particular device shape. And then final one, which I would not be discussing to a greater extent, that is called machining process. So, machining also, there are two type of machining process, one is called conventional machining process, another is called non-conventional machining process. The examples of the conventional machining process is drilling, for example. You can make it cutting and other things, and non-conventional machining process like electro discharge machining, electrochemical polishing, these are like non-conventional machining process, where that you can do this machining process very carefully by application of that electrical energy or chemical reaction route or so on and so forth. So, now coming to the metal forming processes, like what is the bulk deformation process. Now, bulk deformation processes are listed here, that is rolling, forging, extrusion and wire drawing. So, these kind of manufacturing processes, their description and their understanding comes under the purview of the conventional metallurgical engineering principle. So, therefore, I will go little slow in case that you people are from different background, so that you would be able to understand and realize that how these processes are conducted or accomplished in the industrial scale production route of the metallic implants. So, what is the output, and after rolling or after forging, what are the things that you get? It is, you can get metallic sheets, you can get wires, and these wires can be nickel titanium wires which can be used in cardiovascular stents, or you can get metallic sheets or metallic plates which you can use for the fracture fixation device and so on. There is also another technique called sheet metal forming, like you have a large sheet, and then when you do this forming, like you can do deep drawing, stretching, bending, etc. So, this is the first step, that is in the metals manufacturing process, that is solidification. Solidification means you start the material in the molten conditions, then you pour this molten metal through a mold. This is a traditional conventional mold, this is a sand mold, and this once you use this sand mold, then once this metal is to be heated above the melting temperature. The reason being, now if you heat the metal to the melting temperature and then you simply pour the metal into this mold, then what will happen? By the time that molten metal will fill the mold cavity, it will be solidified on its way. So, therefore, you have to give some overheating, that means if the metal melting point is 1600 degrees Celsius, you have to heat them to 1650 or 1700 degrees Celsius, so that the moment it will fill the entire mold cavity, the temperature of the metal mold is still above the melting point, so that it will remain in this one, and then so that it will simply release the heat and it will be densified. So, after this solidification, you get this kind of object, right. What you see immediately, that this part needs to be cut. So, this part needs to be simply machined away, and this is your bulk part. So, the way I am sketching, so this is your bulk part. Now, in this bulk part you get this metallic billet, and this is called workpiece or billet. Now, these metallic pieces you cannot use it for any biomedical applications unless you give them a particular shape, like in the form of plates or in the form of sheets or in the form of nails, those kind of useful shapes. So, therefore, after the solidification, whatever is the output, that will be the starting point for further bulk deformation processes, which can be accomplished by rolling, forging or other bulk deformation processes. So, let us start with that simple example of the rolling. So, what you see here, this is the roll number 1 and this is the roll number 2. So, these two rolls, what you see, these are like rotating in a opposite direction, and then the moment then it starts rotating in the opposite direction, then what will happen, this workpiece, the moment, this is the workpiece I have mentioned in the last slide. So, this workpiece, it will be dragged into the rolls, okay, and it will be dragged into the rolls and it will be coming out. Now, depending on what is the roll gap or roll gap height or h. So, depending on what is the value of h here, that final thickness of the plate also would be the same h. Okay. So, by tailoring this h value or tailoring this gap value, you can have some control over the thickness of the rolled product. This is I call a rolled product. Okay. So, this depending on the rolled product thickness, then you can understand that how much deformation that the metal has taken up, and that is simply, if this is your h1 and this is your final thickness is h2. So, the final deformation would be total height change divided by initial deformation into 100. Okay. So, this is your total deformation that the material. The second thing, what would be the speed? Suppose this is the speed V1, this is the speed V2 of the rolled product, and this is your rolling speed is V3. So, certainly the V1 should be less than V3, should be less than V2, or in other words, exit speed must be higher than the entry speed, exit speed must be higher than rolling speed, otherwise metallic materials will be simply stuck in between the rolls, it cannot come out. So, this comes from the simple physics rule. Now, second one is a forging. So, forging means you have a forged mold cavity here. So, you put your metallic workpiece there, then you apply the compressive forces. By the way, if you go back to this, if you go back to the rolling process also, so these rolls will be experiencing this normal compressive forces, and this normal compressive forces, this is your deformation zone. So, the way I have put this arc, this is your deformation zone. So, this is your zone of deformation. So, at this zone of deformation, the height of the metallic workpiece will be reduced from h1 to h2 progressively, because you see this h2 height is the same as the roll gap height here. Okay. h2 height is the same as the roll gap height h. So, therefore, here the rolling process is also accomplished by or is also accomplished under compressive stresses. The same is true for the forging, because titanium is one of the alloys, titanium alloys, many titanium alloys are used in the forged conditions. So, the forging essentially means you put the workpiece between the two platen, between the die, two upper die and bottom die, then you apply the compression process. In the process of the compression process is the initial height is h1, then after the forging what will happen? The height will be reduced, but the width would be higher. So, if the height is reduced, if the height is now h2, again the compressive strain would be h1 minus h2 by h1 into 100. So, what is the change in the height with respect to the original height multiplied by 100, that will be your compressive strain or compressive deformation. Third one is the extrusion. As the name suggests, extrusion means you have a large block of the material, then with the help of this ram you just put this, apply the compressive pressure, you just force this workpiece to go through the orifice of the die. So, this is your die orifice. So, what would be the diameter of the final extruded tube or extruded product? The diameter would be d. So, this d would be nothing but that extrusion die orifice diameter. Okay. So, this d is very critical, and this v also, that the way that velocity of the extrusion process. Fourth one is the wire drawing. So, wire drawing essentially means that this the definition between extrusion and drawing means, drawing is the only one metal deformation process where the metal experience tensile forces. The way this extrusion and drawing is different, in the case of the drawing you apply the tensile force here. So, you apply the tensile force here at the die orifice end. So, essentially you pull the wire from the other end of the die orifice, and your metallic workpiece will be forced to exit from the die orifice. Okay. Now, some of the things is important in the case of the metals, particularly the grain and the grain size. Now, this is the simplistic description of the grain and grain size. What I have shown here, this is the 3 grain structure, 1, 2, 3. Now, this grain, if you can see this any metals, if you put in the microscope, this is your grain. Okay. Now, if you look at the same grain in the transmission electron microscope with higher resolution, then what you would be able to see? You would be able to see this kind of grain morphology, and this grain morphology is that in grain number 1, these atomic planes, they are oriented in a specific orientation. In grain number 2, that atomic planes are oriented in different orientation. In grain number 3, atomic planes are oriented in certainly different orientation than grain 1 and grain 2. So, what happens as a result, if you consider this grain boundary length AB and BC, AB essentially is the boundary between grain number 1 and grain number 3, and this is the region of the misorientation, because here the orientation of the atom is neither that of grain number 1 nor that of grain number 3. Similarly, if you consider the grain boundary length of BC, here the orientation of the atom is neither of the grain number 1 nor of that grain number 2. Similarly, if you consider the BD grain boundary region, so it is between the interface between the grain number 2 and grain number 3. Therefore, grain boundary region is typically described as the region of misorientation, or grain boundary region is also described of the region of higher energy. Why higher energy? Their atom-atom bonding is somehow locally broken. Inside the grain boundary, all the atomic planes are continuous. At the grain boundary region, that continuity is broken. Therefore, grain boundary region is a region of misorientation. Now, depending on what is the difference in the misorientation, whether it is a small angle grain boundary, then is the angle of misorientation in between 1 to 5 degree or 1 to 8 degree. If it is higher angle grain boundary, then the angle of misorientation even higher, like it goes to 15 to 20 degree. Okay. Now, coming to the little bit description of the mechanical deformation of the metals, like stress strain concept and so on. So, let us first describe very simplistic manner what is tension. Tension means you essentially pull it by equal forces into opposite direction. What is compression? You are actually squeezing the metal by application of the equal force, but in the same direction. What is shear? Shear essentially you are applying same force, but into opposite direction on 2 parallel faces of a cube. So, tension, compression and shear, the material changes differently. In case of tension, the material changes in length, or material increases its length, but reducing its diameter. In case of compression, material reduces its length, but increases its diameter. In case of shear, the material simply there is angular distortion, right, that is the angular strain is theta. So, if you know that strain is nothing but change or ratio of the change in the dimension due to the application of some force divided by the original dimension. So, now another thing that you have to remember, that during all these deformation processes, whatever I have described in last 10-15 minutes or so, forging, rolling, extrusion and wire drawing, this is called plastic deformation process. Now, in case of those deformation processes, volume will remain constant. What it means that at the before the application of the tensile stress, for example, if you take the case T here, before the application of the tensile stress, if the volume is of the material is V1, after the application of the tensile stress at any given instance, if the volume is V2, then V1 must be equal to V2. If it is compression, again before the application of the compression stress, if it is capital V1, after the compression stress it is capital V2, then the volume will remain constant. So, this conservation of the volume is maintained depending irrespective of the mode of whether you are applying tensile forces or tensile stresses or compression stresses. So, let us go through that next one, that is that this is what I have mentioned to you. This is the summary: tensile tend to stress the material, compressive tend to squeeze it, shear tend to cause the adjacent portion of the material to slide against each other. Now, this is the basic definition of the stress. Stress is nothing but force divided by initial cross sectional area. Strain is nothing but change in the length divided by the original length that I have mentioned before. So, this is very important stress strain relationship or stress strain response of a metal. Now, let me explain this little bit carefully. So, you have that initial linear region, then after that it undergoes non-linear deformation. So, this is region is called elastic region. You know that elastic girder or elastic rubber. So, if you stretch it, the moment you release the force, then elastic rubber will come back to its original position. But in case of the metal, what will happen if you put it larger stress or if you put them under larger stress, when it goes to plastic region, then if you go you want to, so any place up to the elastic region, if you release the force, then it goes back to the original force. But if you go up to this level, then you try to go back to the original position, it will never go back. So, then there will be some residual strain that will remain there in the metal. So, this plastic deformation property is very important, because this plastic deformation property will essentially dictate how much deformation that a metal can undergo under the process of rolling, forging or extrusion, this kind of deformation processes. Okay. So, larger the material can undergo deformation without fracture. So, you have to avoid the fracture. Another thing, if you get into more details of these deformation processes, so this is the region called uniform deformation. Uniform deformation essentially extends from the point of the yield. Yield means now metal will not undergo elastic deformation anymore, metal will undergo now plastic deformation. So, from the point of yield to the point of maximum strength, that is called UTS, ultimate tensile strength. Up to the point of UTS, metal will undergo uniform deformation. What is the meaning of uniform deformation? If you go back to the basic description of this tension, what I said, as you apply the load, I am focusing on this part. If you apply the load, the metal will stretch. So, increase in the length will be commensurate with the decrease in the diameter of the cylinder. So, if that kind of relationship is maintained in this particular region, that is the uniform deformation region. So, here that means the increase in the length is commensurate with the decrease in the diameter. That means longitudinal strain and transverse strain, they commensurate with each other, then it will give rise to uniform deformation. In case of non-uniform deformation, which has been mentioned here, this is called non-uniform deformation. What you see in case of non-uniform deformation, that from here this point to this point, the decrease in the cross sectional area is much faster or is much more, or decrease in the cross sectional area takes place to a much larger extent compared to increase in the length of the sample. So, therefore, this region essentially will undergo necking process, and necking is one of the example that it will undergo non-uniform deformation processes. Okay. So, up to the point of the yield, Hooke's law would be valid. Hooke's law essentially means stress is equal to elastic modulus into strain. So, how you can get elastic modulus? It is very simple. You take this any material stress strain response, you take the slope of this curve, then in elastic curve, and then you get the elastic modulus. Okay. The other things which is important, which is like yield point, that is the point that at which the metal will not behave anymore in elastic metal, but it will undergo plastic deformation, that is called yield strength. Now, ultimate tensile strength, as I told you, all this strength property essentially is measured force divided by cross sectional area. So, what is the force? That is what is the maximum force, and that therefore, this UTS or ultimate tensile strength essentially it is the force maximum divided by the initial cross sectional area. What is the force maximum? That is the point of force maximum. So, these are some of the important parameters which essentially determine the mechanical properties of the materials. Okay. Now, coming to the other things, it is called compression test. In the compression test, I have already mentioned that what is the strain, how to define the strain. Define the strain means what is the final height h, what is the initial height h naught, and what is the initial height h naught, that gives you the strain. Okay. Now, you can do it this way, or you can do it in reverse way also, like h naught minus h divided by h naught. This is the compression stress strain response in case of metals. The fundamental similarity or fundamental similarity between the tension and compression is that in both cases it started with a linear response. In case of compression, the metal will undergo non-linear response, but will keeps on increasing. So, in case of the tensile response, then what will happen? Metals will behave this kind of this, but in compression this response is quite different. However, one can also measure the slope of this initial linear curve, and again here the Hooke's law is valid, that is stress is equal to elastic modulus multiplied by the strain. So, the slope of this elastic curve will give you essentially compression modulus. Last one is the shear properties. Now, shear stress is defined again by the force divided by the cross sectional area. What is the force? You are applying force here. What is the cross sectional area? That is the area of this plane, okay, and this is the cross sectional area, and shear strain is deflection element divided by the distance over which deflection occurs. And what is the typical shear stress shear strain response? You get an elastic response divided by followed by the fracture plastic region. Again in the elastic region the slope will give you the modulus of the shear modulus, and then it goes to plasticity, goes to fracture. So, this brings us to the end of the manufacturing and some of the properties of metallic implants.